Hello, everyone, and I will be presenting our work on empirical analysis of privacy preserving learning today. I would like to begin with a quick introduction about myself. My name is Manav Singhal, and I am a rising senior at the National Institute of Technology, Karnataka, India, pursuing my bachelor's in electrical and electronics engineering. My research interests are in the field of machine learning, specifically in the field of reinforcement learning. My mentors for this summer were Pavitra and Olga. I would first like to discuss about the motivation for our project. In many real-world scenarios, the recommender cannot use the feature preferences of a user directly for learning and personalization due to privacy constraints. However, the recommender can learn from aggregated data, as this would uphold the privacy of the user. Therefore, in our project, we aim to study how well our models that are based on the learning from the aggregation of features can predict on test data. I shall now discuss the methodology. We explore the notion of aggregation by using only those features that have seen a minimum threshold of users. We define a private model as that model which has access to the user feature mapping. It uses this mapping to learn and make predictions using the learned weights. This is the current state of VW. A public model is that model that does not have access to the user feature mapping. It will make predictions based on weights from the aggregates, that is, those feature weights that have hit a certain threshold of users, which will be the case after our patch. How do we implement our idea? We make the assumption that the tag of an example is a user ID. For each feature, a 32-bit vector is defined. We calculate a 5-bit hash of the tag of the example for each feature weight, which is updated by a non-zero value. We use the 5-bit hash to look up a bit in the 32-bit vector and set it to 1. When saving the weights into a file, we calculate the number of bits that have been set to 1 for a feature. If it is greater than a threshold, the weights for that feature are saved. This brings us to two important questions. Doesn't the hashing of the tag result in collisions? It does. However, we aim to underestimate the number of tags that are associated with a parameter update. We intend to hit a certain number of users before saving the feature weights. We can do an exact count. However, it is a trade-off between the accuracy and computation. And we believe scoring lower on the accuracy of count, that is, for an example, not storing the weights if threshold minus 1 users are there due to collision, will be the better case. Now this brings us to our second question. How many users do we select as our threshold? We selected 10 users as our threshold. We are trying to find the number of trials for the first occurrence of m bits being flipped out of k bits. This is a geometric distribution. Therefore, the probability of the next bit being flipped given n bits are already flipped is k minus n by k. We know that the expectation of a geometric distribution is 1 by p. Hence, the expected waiting time until m bits are flipped is a summation from 0 to m minus 1 of our expectation k by k minus n. On calculating our expected waiting time, we found that the waiting time for flipping 10 bits out of 32 was 11.76, while it was 22.2 for flipping 10 bits out of 11. Hence, we went with the former case and flipped 10 bits out of 32 feature bit vector. This statement goes on to imply that we need at least 12 unique users in expectation to flip the 10 bits out of 32 bits as in our case. The achievements of our project was that we completed a patch implementing our idea on my fork. We ran the CB simulation for content personalization to compare the model performance. We tested our patch on the OpenML click prediction dataset. We believe this patch is a stepping stone to privacy preserving learning. While attempting privacy preserving prediction, we figured out the implementation details for privacy preserving learning. I shall now take you through our notebook for the content personalization. This notebook is very similar to the one which is found on the VW website, where you're trying to simulate the content personalization with contextual bandits. We define a reward and a single cost function, wherein you could see that the even users like politics in the morning and music in the afternoon, while the odd users like sports in the morning and politics in the afternoon. After that, we have certain functions which help in converting to a VW friendly format the input and finding the custom PMF for the values of the list of the actions. Further, we also have a function which returns the action and probability of choosing it. The run simulation cost function then generates the simulations and helps the learner to learn. We have 10,000 iterations which we ran. Here you see the two different learners, VW and VW1 being declared. As you see, VW1 has privacy activation being written, which is the command line argument for activating the privacy which we've implemented. We ran CB type IPS, which is inverse propensity scoring, and using CB explore ADF, we used the epsilon greedy exploration algorithm and a value of 0.2. After we saved this model, we went on to read the model and predict on another simulation the values and then plotted the graph to compare the performance. I shall now show you the results of our comparison. As you see, when you had quadratic interactions, we found that the click-through rate performance was nearly half of our public model. The reason for this can be attributed to the fact that certain features, such as the users into the time of the day or users into a specific action article, will in no way go on to hit 10 users, which we want for our public model to save those features. Therefore, we had a near half drop in performance over here. If you see the lower graph where there is no interaction, you see that the performance is very similar in the private and the public model because such features are not being generated. In a similar case as in cubic interaction, we found the performance to be nearly half of the private model, as you saw in the quadratic interaction case. After that, we went on to experiment with two action features where you have an action article X and an image content Y. We experimented with various cubic and quadratic interactions, and on the right you see the number of features saved for the public and the private model. We again saw a drop in performance, as in the case over here where you have quadratic and cubic being tried together. However, now when we went to the regime of the real world data sets, that is the OpenML click prediction data sets, we tried 4 of them ranging from a 40K sample size to 1.9 million sample size. On the left, you see the average loss in the testing case being plotted against the number of examples, and on the right, you see the number of features being saved. Here is where we saw that there was a competitive performance for our public model versus the private model, even bettering it in a few cases. If you see that the average loss difference is significantly lower between the two models over here, despite the major difference in the number of features being saved. Why does such a thing happen? We attribute this behavior to something similar to that of L1 regularization, where the features which are not that important for our model are being dropped. Hence, there's some sort of filtering of feature selection taking place, resulting in a public model performing equally well as a private model. This was the case in CB type IPS. We also tested with CB type MTR over here and found a similar performance between our public model and private model on the OpenML click prediction dataset. I shall now take you through our future work. We wish to implement the patch for save resume, where the auxiliary weights are also stored so that the training can be resumed on the saved model. We also aim to work on integrating the patch into VW Master so that all of you could play with it. We also aim to work on the aggregations in the online setting, that is, the privacy preserving learning, as currently we are only working with the saved models. This work would not have been possible without my wonderful mentors Pavitra and Olga. I would like to thank them for all their support. I would also like to convey my special thanks to Jack, Marco, and Paul, and my fellow RLOS peers for this fun learning experience. I would be happy to take any questions now.
Excellent. Well, thank you for the presentation, Manav. Our next presenter is Nishant Kumar, who'll be talking about VW parallel parsing improvements. Take it away, Nishant.
Am I audible and my screen is visible?
Yes, and now we can see your screen.
Okay, cool. So I'll be presenting our work on parallel parsing as a part of the Reinforcement Learning Open Source Fest. Um, I'm Nishant, and my mentors for this project were Peter and Jack. So let me just quickly introduce myself. I'm Nishant. I'm 21. I'm a rising senior at ITBHU, Varanasi, India, and I like to the things that I like are mostly AI, mostly reinforcement learning, multi-agent systems, open source, unboxing gadgets, and driving on rainy days. And here's a link to my website. So onto the project. So I'll give a quick background info about related to the project. So VW is a fast, very fast library, but in this project we try to make it work even faster. So VW has two components, the parser and the learner. The parser accepts four input formats. We have text, cache, JSON, and flat buffers, which was recently added last year. And the parser is usually more than one time slower than the learner. And that's what our project deals with. So here's a quick layout of the operations that we have currently. So we have this parser thread, and it's just reading a line from the input file. It's parsing it and it's pushing it to the queue, and the learner pops an example from the queue and it learns on it. So basically, the parser performs the reading and the parsing steps, and the learner performs just the learner just learns on it. And as you can notice, there is a single parser and a single learner thread. So this project is a continuation of the last year's work done by Cassandra, and the major milestones achieved in the last project was parallelizing the text parser and separating the I/O operations from the parser as a separate thread. And here's a link to the project. So the outcome of last year's work was this, and we'll be building upon this work. So there are two things to notice here. The first is that we have a separate IO thread, which is responsible for reading lines from the input, and there are multiple parser threads which work on that, parse that example and pass it to the learner. And there are two queues here. So the motivation for this project is kind of related to similar to the last year's project, and that is to reduce the first is to reduce the parser bottleneck, and that is because the parser takes much more CPU time than the learner. The next is to better utilize the CPU resources, and by CPU resources we mean the CPU cores basically. And the third is to separate the logically different operations into separate threads. We do that for a better layout of operations and for the ease of multi-threading, because it's easier to multi-thread if you have it separated. And a good example would be separating the I/O operations from the parser. So the goals achieved for this project were as follows. We improved the text parser's performance. We added support for multi-threaded cache parsing, for JSON parsing, which was a stretch goal initially. We also added support for multiple passes and multi-line examples with multi-threaded passes, which was again a stretch goal. And finally, we benchmarked the results. So let's just quickly discuss the major changes that we made in this project. So the first is that cache now is written and read in a kind of a special way to allow parsing. And here's the reason. So in text, we have this delimiter \n. It kind of acts like a delimiter. So the IO thread basically looks for this new character line, and it recognizes that this is the end of an example. But for the cache input, that's not the case because it's written in binary. So we do the IO thread doesn't know where to stop. So in order to help it, understand where the example ends, we prepend unsigned integer in the beginning, which contains the number of characters for the next example. That's how cache is written and read. So the two more major changes that we made were relocating some functions. So the pass counting logic, the setup examples, and the cache writer are now shifted to the learner thread, and that's done because in order to better handle the root conditions. And yeah, so like a future work would be to create a separate thread for these operations. And the other thing, in order to support JSON, we need to use a vector of examples instead of a single example throughout the parser, and that is done to maintain the example sequence for JSON and to handle multi-line examples. So here are some benchmark results. So before we discuss the results, let's discuss the parameters. So these are the two terms we'll be using throughout our discussion of the results. So ST stands for the single thread, which is the original VW master branch containing a single parser thread and a single learner thread. And MT stands for the multi-threaded version, which contains a single IO thread, a single learner thread, and multiple parsers. So for these, we'll be comparing ST versus MP, and for the three input formats, cache, text, and JSON. And the graphs will be time versus the number of parser threads. And yeah, the results will be averaged out over 10 to 100 runs. The results are on the release build, and we use a 32 physical core machine. So here are the results for cache. So there are some terms we should discuss. 0.1 M stands for 100,000 samples, and the results are averaged over 100 runs. 1 M stands for a million. So the dotted lines here represent the single-threaded version, and you can see that it will remain constant since it doesn't depend on the number of passes, while the bold lines represent the multi-threaded version, and we can see that as we increase the number of passes, the time taken by the multi-threaded version decreases. So finally we receive a 25% improvement over ST. Yeah, so that's cache. Now we move to text. So here there is two changes that we observe. The first is that then if we use for cache we had if we use two parsers, the performance was not that great. So like it didn't go below ST. But now we have a performance boost, which is even for two parsers, it performs better than the single-threaded version, and we see an overall of 60% improvement in performance over ST. So, and finally for JSON, we see an even greater performance improvement around 68. And in the next slide, we'll discuss why this pattern is emerging. So here are the call grind results. So call grind is basically a tool which measures the CPU time taken, CPU time percentage taken by each of these functions in the source code. So here are the results for call grind when we ran ST over the cache, text, and JSON input formats. So since these are single-threaded, we just receive the parser and learner. There is no I/O. So yeah, so for cache, we see that the parser takes up about 76%, which is kind of less compared to the text and JSON. And the JSON uh, parser takes the maximum amount of time, CPU time, and that's why we see an improvement of 68%, which is the highest, followed by text and cache. So that kind of explains why we see that results, because the 96% is each being
Nishant, you have
divided.
about 1 more minute.
Okay. So I'll just quickly discuss the challenges. Maintaining data file ordering using multiple parsers, maintaining pass count in the parser thread, dealing with multi-line examples, and identifying contentions. And my learnings for this project were I learned about mutexes, condition variables, atomic operations, using the GNU debugger for multi-threaded code, profilers like valgrind, and mutrace for tracing mutexes and logs. So here is the outcome of the project. This PR contains all of the work. For future work, we have multi-threading the fact buffer parser, improving the single parser performance, cache performance, and bringing it close to about 10% of S3, modifying the unit test to account for multi-threaded operations, and finally creating a pull request to the VW master branch with all the issues sorted. So to know more, kindly visit this website. I've mentioned all the details regarding this project. And thank you for listening. I'm open for questions now.
Could you go to the slide with the call grind results for a second?
Oh, sure. Yeah.
Okay. So the learner is only like 5%. Okay, cool. So shouldn't you see like a lot more improvement then for each additional thread?
Yeah, so that kind of is expected, but again, like if we spawn a number of threads, we are kind of increasing the complexity and the number of operations. So I mean that's why we kind of observed the 68%. So actually, I discussed this with Peter, and he kind of agreed. So
Okay.
maybe that.
Did you study like lock contention and things like that?
Yeah, so we did use mutrace for identifying like which kind of where the where the functions were logged, or maybe there were contentions. But like I think that was like kind of taken care of. So
Interesting. Thank you.
Thanks, Nishant. Our next speaker is Vishal Vinod, who'll be talking about VW feature transformation without redeploying the source.
Hi everyone. Is my screen visible?
Yes, it is.
Okay. So I'm Vishal Vinod, and I've worked with Eduardo on VW feature transformation without redeploying the source. I'm a master's in computer science student at UC San Diego, and my research interests are in continual learning and domain generalization. So first of all, the motivation for the project is that we want to enable data scientists to iterate faster without having to manipulate the input data file. So whenever an example is passed on to a learner, we want to enable manipulation to those examples without having any overhead or manipulations from the data scientist side in the input file. We do not want to redeploy the service that produces the incoming data or examples. So we want to do it in memory. And if required, users should be able to add new manipulations to VW. So different types of feature manipulations like binarization, different types of normalization should be able to be added to VW. And one other motivation was that once the AutoML reduction is implemented, we will be able to compare two different models with different manipulations. So this work will integrate well with that so that we can modify the examples in memory using the reduction we have implemented. And lastly, feature modifications will enable quick prototyping of different mutations and also enables comparison of performance. So the goals for this project is to simplify feature modifications by implementing a generic reduction. So right now, for every transformation that needs to be implemented, a new reduction has to be implemented, tested, and added to the reduction stack. So we want to simplify that process. And we also want to avoid transforming the data by other means. So it should be a safe manner and there should not be any performance hit because of other means. And we avoid redeploying the source that produces the examples. And also, we also need to allow the users to customize the behavior. And lastly, we will also allow label mutations so that we can transform tasks or also apply other types of feature engineering. So an overview of VW, as Nishant also had presented. So we have multiple parse threads that read and parse examples and pass it on to the example queue where the examples are parsed. So and then it is passed on to a learner thread where the learning occurs. So the example schema is such that there are a collection of examples, and each example has a namespace where each namespace has multiple features, and there's one label for each example. To go a little deeper, so we see what a namespace has. So a namespace has feature count that says how many features it has, the namespace name, the feature group, a namespace hash. So hashing is what is one of the features that makes VW really quick, and the features in. And feature by themselves have values, a space name which is used by the audit string so that we have a more interpretable result for debugging, sum of feature square, and the feature index itself, which is the hash. So the design for this project is that we will first start by implementing a delete feature functionality. And once that is implemented as a reduction, we would modify it such that new modifications like renaming a feature or adding a logarithmic modification or binarization or different functionality like that could be added by just registering a function that can perform these functionalities. So there is just one reduction, and we create multiple functions that are then registered with this reduction. So new transformations can be registered with the reduction. So the mutation on the input is on the input example itself rather than on the model. And the design is such that we would add command line arguments, like you would have a mod feature, which would modify the specific feature name, modify the namespace specific to this feature. So if it is an empty namespace, then we would just pass a space. So and we also add the functionality. So del ftr would be deleting that feature. Renaming would match the hash and then rename it. Similarly, modification of value would modify the value for that feature, and so on. So binaries, there's a threshold and log base, and also for labels. So a little overview on the implementation is that we mutate the features without having to redeploy the source. So first of all, as mentioned, we would delete a specific feature. So we match the feature hash with the namespace and remove the namespace if it is empty. And then we would remove the index based on the matching index and modify the audit string to reflect the deletion. And we would test this by checking if the hash matching works and if it is efficient. And we also would also further test by instantiating different learners with and without the delete option and compare their results. So that would be clear in the demo. So similarly, we would have the same for renaming, binarization, and log scale modifications. So here's a short demo of the same. So yes. So here we have one sample file with 10 examples, just a toy example for the demo. And here we have one where the features that we want to delete are manually deleted. So this demo would compare the performance with the delete feature and without it, and then the results should match. So here we see we pass sample.data, that is this file. We modify P, which is of the Z namespace. So these would be deleted. And we enable the feature manipulation, and we would check this without audit. And similarly here, we would check for manually deleted text, but without any of the modifications. As we can see, although this has a lot more features, 27 to be exact, we are able to delete the features and get just 19. And if you notice, these are just logs mentioning that we've deleted the feature with the specific hash that has been matched. And as you can see, the predictions match across the manually deleted file as well as the one that we have deleted, showing that delete feature works. So similarly, we would have key name. Yes. So here we would be comparing against this file with the exact same feature, that is P in the namespace Z, and we would rename it to A. And in this file that we would be comparing without the modification, all of them have been renamed from P to A in the same namespace. So as we can see, we have the exact same average loss and the predictions across both. And if we run the same with audit, we see that all the files, although it is P here, it has been renamed to A. So similarly, we can have the same for binarize as well as so this would binarize the label. So we have the label has been modified depending on the threshold added. So this is a short tutorial on how a new mutation can be added. So there are a lot more mutations that can easily be added. So first, we have 3 functions that can be referred to in the reduction. So delete feature would modify the example, also save a copy of the example, and then have the feature matching and delete the specific features with different checks. So modify feature value would modify the specific values and modify label for the labels. So referring to these functions, you can create your own calling function that just takes in an example and then the feature data structure that we have created and make this modification that's required. So so once that function is implemented, you just have to add it, add an option that would modify it, and then pass it to man feature, which takes in a functional pointer. So whatever was implemented can be added, and it would automatically be used up in the reduction, and then you could test it. So the learnings for this work was getting to know more about how to make how the reduction stack works and how that's a very clean and fast implementation, and how the example parser works. So initially we had prototyped modifying the example in the parser in the parse stage itself, but then that did not pan out well because we would need to save it again. And so yes, so I also learned more about the learner threads and how interactions work and how feature manipulation would associate it, integrate with interactions. So working on a C++ project, learning more about performance improvements, generics, and different techniques. So the next steps for this would be to have more extensive tests with larger data sets to merge the commits to the main branch. And we would also create a tutorial where small or new, more relevant mutations can be quickly added. And this would also have to be compatible with the AutoML reduction that Varun had presented. So we would instantiate 2 learners and compare the results between them. And we should also be able to express the mutations with JSON instead of the command line. So future work, which we're looking into, is looking into how namespaces and feature groups with full name interactions affect this project. And also, as I mentioned, we would be able to register callable functions with the feature manip, and we would see how JavaScript or Python mutations can also be included. So yes, that is all. I thank Eduardo for all the time and support during the summer. If there are any questions, yeah, you may.
So I have a quick question.
Yes.
So assuming this is like at the very top of the stack?
It would happen after the scorer is called. So interactions has already like the setup for interactions has already happened.
I see. So if you had interactions, they would not know about the new name, or they would know
Yes.
about them?
So yeah, right now interactions have a setup happens before, so that wouldn't be happening. So that is one thing we would look into before merging the.
Got it. Cool.
Yeah.
Thank you. I think Sid has a question.
Yeah, can you guys hear me?
Yes.
So I guess I have two small questions. Well, maybe one small question, and if you have time, I can ask another one. The small question is: do you think that VW's feature hashing approach made a lot of these changes possible? In the sense that if it didn't use feature hashing, would this be a lot trickier to do?
Likely yes, because now that namespaces are there, we will be able to delete features that are specifically part of specific namespaces, which gives a lot more functionality. So the namespace hash as well as the feature hash is better. But since it's an array, so we wouldn't be able to modify in like a random access. So we would still have to pop from the back. So yeah, that is all right. But yes, the hash does help.
I see. Okay. I guess at a higher level question, which is how should I think about doing these kinds of changes on the fly? I mean, you mentioned, I may have missed it because my audio wasn't great, but I think you mentioned switching from, regression to classification. I mean, doing this on the fly, this will have serious implications on what the model will do during that transition, right? Its performance. Are you kind of saying, do this at your own risk? Or are you thinking about that problem as well?
Hey, Sid, if you don't mind, if we can take that to chat, because we're running a little bit behind.
Oh, sure. No problem. Yeah. Feel free to cut me off. Thank you.
Thanks, Vishal.
Thank you.
Next, we have Mónika Farsang, who's going to be talking about safe contextual bandits.
Thank you. I share my screen. Can you see it now?
It's coming up, yes.
Okay, great. So, hi everyone. My name is Mónika Farsang, and I would like to present our reinforcement learning open source fest project called Safe Contextual Bandits. This is a joint work with Milena, and we have two mentors, Paul and Vangda. First, I would like to talk about the motivation and the orientation of this project. So the motivation behind this project that contextual bandit algorithms optimize the mean value of the reward distribution without paying attention to the worst case scenarios. But there are many safety critical domains where it would be better to use a different approach. For example, minimizing the latency or maximizing the throughput in a network tuning, or in the case of item recommendation to limit the negative feedback. Or another example could be query optimization, where maximizing the speed of the worst performance could be important. So our goal is to implement safe contextual bandits, which focus specifically on the worst cases. For this, we use conditional value at risk, CVAR for short, and this is the direction of my work. CVAR means the expected return in the worst Q% of the cases. This term comes from finance, where it is used to evaluate the market or the credit risk of a portfolio. Contextual bandit policies typically optimize the mean value of the distribution, and they result in a degraded worst case behavior for better average case behavior. But instead of this, we would like to optimize the CVAR of the policy returns. And with this, we would like to get slightly worse mean rewards for much better results in the worst case. So all in all, we would like to optimize the average of the tail instead the average of the whole distribution. So our goal is to create safe contextual bandit algorithms, and our expectation is to avoid bad actions and maintain safety. CVAR mathematically has a dual formulation. Basically, this is off-policy learning with a modified reward, where this modified reward is passed to the contextual bandit learner. And we have a free parameter rho. This is where the cutoff point is in the reward distribution. This optimization is not a saddle point problem, so it can be considered as a relatively simple approach. And we are working together with the optimizer, not against it, and we are leveraging this dual representation while we are setting this one-dimensional parameter rho. So the key question of this project was how to set this rho parameter. First of all, we set this in Python, and later it will be easy to port to C++ and VW. And it was not about setting only one row, because we are receiving a data stream, and we adjust row as we go, so in an online manner. And as I mentioned, this is a simpler optimization problem, so there could be several methods for this. But we decided to use a no-regret algorithm called FreeGrad, which seems robust. And during our work, we used the COBA package to evaluate and compare the algorithms, and we used OpenML regression datasets. From now on, I would like to show you some of our results with this CVAR optimization approach. In COBA, we compared our CVAR learner with a random and a VW learner. And here you can see the reward histograms of these three learners. And these histograms show what we expected, while the random learner can be considered as a baseline and shows the behavior without learning anything. The VW contextual bandit learner and the CVAR learner are able to achieve higher rewards. And while the VW contextual bandit learner is better at getting the highest rewards, our CVAR learner performs better at getting less lower results compared to the VW learner. This slide shows the average rewards on the left and the CVAR values on the right. Here, these are the average rewards in the worst 20% of the cases. And on the x-axis, you can see the same learners as on the previous slide. So the random, the VW, and the CVAR learner. And when we look at the average reward and the CVAR of these learners, the random learner performs poorly in both cases, and the VW and the CVAR learner have pretty similar results. And if we zoom in and we only care about the difference between the VW contextual bandit learner and the CVAR optimizer learner, we can also see the confidence intervals here. And here are the upper and the lower bounds of these values. And our results show that using CVAR can result in a slightly worse average case behavior in exchange for better worst case behavior than the VW learner. And this was exactly our goal with this CVAR algorithm. And it's also important to note that these confidence intervals don't overlap. So all in all, this is a really, really good result of this CVAR learner. However, as a limitation, I would like to present you this result as well. Interestingly, we found that our CVAR learner has some difficulty with extreme quantize. So for example, here with Q equals 0.1, here it wasn't able to adapt and couldn't achieve better CVAR results than the VW learner. Maybe with more tuning, we could achieve better results with this, and this is something that we want to investigate in the future. But in general, it seems like that running the CVAR learner with extreme quantize is going to be more difficult. And having intermediate quantize, like between 0.2 to 0.4, they look more promising. And about some takeaways and the future plans. First of all, it was a huge opportunity and an exciting project, and I feel like I learned a lot. And it was great to see how to break down this bigger idea and project into smaller, manageable steps. And I would like to continue this contribution. And regarding the future plans, our goal is to switch to a real-world data set to see if this CVAR optimization approach is working there as well. And we want to switch to the query optimization dataset specifically, which is provided by our mentor Wangda. Here, we would like to achieve better runtimes in queries, and we would like to change the query plans. And by simply optimizing the average runtimes could result in slower queries. And our goal is to maximize the speed of the worst performance. And finally, huge thank you to my mentors, Paul and Wangda, for their help and support during this project. And it was a truly great experience. And thank you for your attention. And if you have any questions, I'm happy to answer.
Well, thank you for your talk, Mónika. And to finish us off, we'll be speaking Milena and Mathew, also talking about safe contextual bandits.
I apologize. Can you guys see my screen?
Yes, we can see it. Now we can hear you.
Okay, perfect. Sorry about that. So hi, I'm Milena, and I am, I'm Milena. I'm an undergraduate at UC Berkeley, studying electrical engineering and computer science. And I worked this summer with Paul and Wangda and with Mónika on implementing constraints. Specifically, I worked on chance-constrained policy optimization. So what is that and like what's the motivation for it? So Mónika talked a bit about, why we might want to constraint and about worst case behavior, but there's more than one way someone might want to limit unwanted behavior. So maybe in some situations, it's not sufficient just to limit worst case behavior, but you want to put a hard limit, a complete limit on some sort of behavior. So take, for example, ad placement. If you're a web browser like Bing, you probably make most of your revenue off of advertising. But if a user sees too many ads, they'll probably just turn off your browser. So you want to optimize for the amount of revenue you earn by placing more ads, but up to some sort of hard limit. Whatever that limit is that will cause your user to just turn off your browser. So we want to optimize our reward while respecting some sort of hard constraint. In this case, the maximum number of ads the user sees. And this sort of problem is present in a lot of different domains. So that was kind of the motivation for developing this. So how do we implement this constraint in practice? Typically, a contextual bandit learner uses some context X to select an action A and in turn receives a reward R. But when we're trying to implement a constraint, we need to figure out whether a given action violates that constraint or not. So we have additional feedback Y, which could be a single value or it could be a vector. And so we can formulate a constraint by creating this function G. So in our case, we say that if this G function, when given this additional feedback, returns a value less than 0, that action does not violate the constraint, whereas if it's greater than 0, it does violate the constraint. So our goal is to maximize our reward, our expected reward, while being subject to keeping this constraint value below 0. So trying to not violate the constraint. And our G function is vector valued if our feedback is a vector as well. So in practice, what this involved was implementing this constraint in a learner. And then I used FreeGrad, which Mónika talked a bit about. It's a no-regret algorithm to choose dual variables. So I used that. Actually used Monika's implementation of it. And then I passed the modified reward into the unconstrained learner. So the benefit of this type of approach is that you can put a constraint on any learner. Since we're modifying the reward and passing it into a learner, you can kind of stack this constraint on an existing learner. So I worked on implementing this in COBA, which is a great package that Mark Rucker, an RLOS participant last year, developed. And it's quite great as both a benchmarking framework and for being really easy to implement new learners in. So a couple of things I did was to implement a new constrained simulation type, which was similar to the existing Lambda simulation that allows you to kind of, pass in your own inputs and stuff. But in addition, add an arbitrary length amount of feedback. So instead of just getting the reward each time, you would also get these feedback parameters. And then I structured my learner so that it took in another learner as input. So you could stack the constraint on basically any learner implemented in COBA. Okay, so a little bit on how that worked out. So I didn't get the chance to work with a real data set, so I created my own simulations to kind of test this out. So this plot is an average over 4 different runs, and it shows progressive reward. So in this simulation, there were 2 possible actions. One action had reward 0.5, and that obeyed the constraint, and one had reward 0.9 that violated it. Actually, this reminds me. So one last thing about the software is that instead, to avoid passing in functions as arguments, instead of passing in just the feedback, I passed in the G values. So the output of that formulation of the constraint that I discussed on the the implementation slide. But yes, back to this. So 2 possible actions, one that's high reward but violates the constraint, one that's lower reward that doesn't violate the constraint. So this blue line that you see here is a random learner. So, kind of our baseline for comparison. And then the orange line is a VW learner using bagging-based exploration. And those vertical orange bars on that line represent the standard deviation. So you can see that the learner is clearly learning to obey the constraint, picking the lower reward option, even though, it picks the non-constraint violating option, even though it has significantly lower reward. And you can see that as the interactions go on, that standard deviation gets lower and lower, which means that, even if the speed which it learns constraint varies, it does seem to eventually learn the constraint. So this is the same simulation, but instead of averaging it over the whole run, it's averaged over every 10 iterations, so you can see how quickly it drops. Of course, this will vary a bit from a run, but it seems to learn the constraint pretty quickly, and I think it's potentially promising. So what if we get a little more complicated? So I added some Gaussian noise to the G values, meaning sometimes that the high reward action would not violate the constraint, and sometimes the low reward action would violate the constraint. And I was wondering how that would affect learning and its performance. And from this plot, we can see that the standard deviation is much higher, but it also seems to learn the more frequently non-constraint violating option, even though, it seems to be learning significantly slower. Okay, so I talked a little bit about implementing, multiple feedback elements. So how does it actually perform in that situation? So in this simulation, I created 3 possible actions and 2 constraints. So one action has a high reward, 0.9, but it violates both constraints. One action has reward 0.6, but it violates one constraint. And the last option has reward 0.2, but it does not violate either constraint. And so I was interested in seeing if, maybe our learner would pick the middle ground or something, to optimize, is it really obeying these hard limits, or is it, doing something in the middle? But we can see that it really does obey those hard limits. It quickly chooses the 0.2 option. So it doesn't try to take the middle road. And again, this will vary, like the point at which it learns this will vary from simulation to simulation, but you can see that it pretty quickly learns that behavior. And lastly, you can implement this constraint on, you can put a constraint on any learner in COBA. And I think there's a lot of room to explore here. I didn't, get a chance to stack it on everything, and especially since I was working on these custom simulations. I didn't get too much of an opportunity to, play around with other learners, but, I think there's definitely room for exploration on what works and what doesn't here. Note is that for a constraint to be effective, the learner has to have a reward-sensitive exploration, meaning that it should stop exploring areas with low reward, or in our case, areas that violate constraints. So, for example, I tossed a constraint on this epsilon grady bandit learner, but you can see it doesn't really learn the constraint, which makes sense because the exploration for this learner is reward oblivious. So in conclusion, adding constraints to a learner seems to significantly reduce constraint violating behavior when that learner has reward sensitive exploration. And I think it's there's definitely room for more exploration, and it seems like a promising direction. So I guess the next steps or extensions to this project would be to test on a real life data set. I also have the changes to implement this in the forked repo of COBA. So hopefully getting those pushed to the actual repo. Yeah, so those would be the last things to wrap this up. But that's it for this presentation. Is there any questions?
Yeah, I guess I have one. So are the constraints dependent on like context somehow? So like it depends on the action. You pick an action, you get different rewards, but they violate constraints. But is it also somehow dependent on like the global context and the action?
Yeah, so my simulations, in my simulations that I created, they were not dependent on the global context or anything like that. And of course, this uses the assumption that the environment resets after every iteration. However, if you wanted to, take advantage of, if you wanted to implement something based on the context or that type of thing, I think it would be a matter of structuring this G function correctly. Yeah, I guess that's one way to put it. So if you structure that G function in a way like that, if you wanted to incorporate the context, I believe that would work. Hopefully that answers your question.
Yes.
But I did not do that here.
Okay, thank you.
Okay, thank you, Milena, and thank you everyone who presented. Thank you for joining us this summer, and I look forward to seeing what other contributions you have to machine learning as a whole.